Okay. Okay. How's everyone doing? There you go. Weekend? Is it an exam or something? Yeah. Oh, thanks. I don't. Um, what were we doing at the end of last class?
Last class we were on chapter 4 still, right? We were on the cancer stuff, I believe, right? But
Yeah. We're getting to the big one. The big one is the one that we're gonna start every lecture going over it and looking at all the different components. So hopefully you have this in your book already, and you are beginning to sort of like think about what it means. We'll do probably energy today too. Hopefully we'll get that far. So let me write it down in tensor notation. And you can tell me what each part means. First piece is this. What's that?
Studying the curves.
These are steady and inverted terms of what?
The motion of
The motion, specifically the momentum, right? Because it's a combination here of the density. Velocity, good. So what's it equal to? We're not reading off the textbook. We just have to think about what it means. I'm reading from the textbook, but you should be thinking about what creates momentum.
change in pressure.
Change in pressure, so pressure gradients.
The body force on that.
Yeah, body forces. What are body forces?
Something that causes. System you're concerned?
Sure, but what? What are the body forces?
Oh.
What's causing the body forces? What force is causing the body?
Well, this one gravity.
Gravity, right? The one that we wrote with G. Right? So the body forces typically we'll see are gravity. Sometimes you use electromagnetism. But to your point, right? You think about the jelly bean, it's moving the whole jelly bean, as opposed to moving part of the surface. Good, what else? Okay. That vector term, that's the motion that bringing momentum from point A to point B. we have changes in the momentum with respect to time. These are due to the fact that there are pressure differences, right? And it's due to the fact that there are body forces. And then stresses, shears. Good. So this is the way that we can deal with momentum of a fluid. You can now simulate a fluid. If you can find a generalized solution to this equation, you will win $1 million. This is an outstanding problem in what is called the Fields Prize, so mathematics, because there exists no general solution. Now, if we make some assumptions, we can find a whole class of beautiful solutions. And we use it's quite common, but they require simplifications, right? Why do they require simplifications? Mostly, it's these fuckers right here. Okay? It's the momentum and the derivative of the momentum. Or another way to look at that is momentum times a momentum. This is a nonlinear equation in the velocity. Linear equations in velocity, they tend to have pretty straightforward solutions. Over here, it gets even worse, right? Here I have derivatives of derivatives, right? And derivatives of the momentum, okay? So these types of shears and stresses in the fluid make very simple solutions impossible. So what we'll do is we'll try to look for simplifications here, where we can. We'll look for simplifications here, where we can. And we'll look at the relationship between each of these terms. So as a physicist, when you see something like this, right? When you see an equation, you can ask yourself the question, what is the dominant term? So depending on the context, you might say that the most important thing are the pressure differences. When would that be true? Just a physical example of when pressure differences are important. Don't think about the equation, just think about the world in which, what's that? Okay, altitude. So that might be really important, say, for body changes. Right? Because that's not, going up and down, we haven't really described the fluid as a whole. Yeah, but we can say, okay, body forces might be really important when we're thinking about a circumstance in which we vary largely in altitude. What about pressure differences? Pressing stuff? Do you have a physical example?
Yes, if we were gonna talk about like the car, right, with the.
Good, like a piston, right? Yeah, so maybe there's something in a pipe, right? And so it explodes and it pushes the pipe out, big pressure difference, right? So then this might be the dominant term. All the momentum is coming from the motion in the pipe, the pressure in the pipe. Here, let's say pressure difference is not that important if you have some really, really tall gas and you're just comparing different altitudes and it's, vertically structured. And in fact, we've seen this before. Because if this is not important and this stuff's not important, we have a relationship between these three terms, the stuff on the left-hand side and the stuff here in the middle, right? So we can always look at these different terms and try to understand how big they are relative to one another. Okay. So the first thing that we can do here is to think about what happens when the fluid is incompressible. So what's the definition of incompressibility? Good. Yeah, something is zero. Good. What is that thing?
Del dot U.
So if del dot u equals 0, then you get a simplified form of this. Okay, we can use the vector notation just to make this nice and tight. My del P plus rho G, that's a vector, plus mu del squared U. What's this type of equation called? Laplacian, right? So these things are solvable. It's a Laplacian if it equals 0. If it equals something, it's a Poisson equation. And usually the way that we solve these is by considering, you can solve them numerically, and you can just iterate over the solution until the shape becomes what the rest of it's supposed to be. We'll see that in computation. Okay, we can also simplify this piece here by remembering that there's the definition of the vorticity. Do you recall the vorticity? What that is?
I don't think it was 0 is.
What is omega?
Oh, del crossing.
Del cross U. So we can take advantage of the fact that the definition of the vorticity and del crosses, they have this beautiful little symmetry. So we can write this thing if we want. This is also equivalent to minus mu del cross omega. That might seem a little weird to folks. So let's recall that for an incompressible fluid, what we're saying on the right-hand side, that very last term, this is the divergence of the strain rate. So what I mean by that is it's describing how, for an incompressible fluid, we don't have the ability to switch it in or out. There's no rarefication, no expansion. So this is just having to do with the deformation of the parcel, right? And so what this says here, this is the cross product or the curl of the vorticity. So what we're thinking about when we think about the Laplacian of the velocity or the curl of the vorticity is that these two they're relating the let's see how I say this properly. The rotational changes, the mixing or the changing of the fluid to the velocity distributions therein. If the fluid has no viscosity, it's an inviscid fluid, we get an even easier simplification. So now let's set mu equal to 0. Now you get rho du dt is equal to minus del P plus rho G. Have you ever seen this before? Oh, yeah, but I lost the term at the end. Ever seen that before? So that's Euler's equation. Okay. And what this is essentially saying is the only ways to generate momentum in an incompressible inviscid fluid, and inviscid means there's no viscosity. Only thing you can do with that fluid, is have pressure differences or body forces. Because that fluid does not communicate through shears. What would that look like? Let's take a fluid, right? Let's imagine that you have some box or some jelly bean or whatever, and you run your hand across the top of it. It's an inviscid fluid, nothing happens. Your hand moves across it, no problem. You can start it going by putting that fluid at the top of the hill and letting it roll down. That's the second term. You can also start the fluid moving by pressing on it, right? Because it's incompressible. So now that pressure is transmuted through the fluid and causes the fluid to move. Right? Without compressing, right? So the whole box moves.
So shape could change.
Well, the shape could potentially change.
What I mean by that is like where it stays.
Good. Okay, so that's how you go from very hard to overly simplified, right? In practice, we won't really use this unless you have some form where viscosity ends up being very minimal. Okay? We can also make this harder. Let's see, do we want to do that now? So this is, I wanted to end this part of, this is supposedly week 3, lecture 2. So we're clearly well ahead of time. No, it's a joke. We're extremely behind, but I think, it's still helpful. What I want to do now is I want to show you, we did that. We did that. Wait. Oh God. Oh God, what have I done? Okay. Yeah, well, maybe we're not as far back as I thought we were. Because we did all this, right? Okay, we just did that. All right, we're chilling. Okay, wait. So I guess I just didn't edit these slides very good. All right, here we go. All right. My favorite part about this part of the class is look how many slides we do per class. Okay, so now we could talk about some modifications to the Navier Stokes equation, because there in fact are more ways to create momentum than just stresses or shears. But I think it makes more sense to sort of write down all of the conservation laws first, and then we'll come back to one of the primary ways that we create momentum in a plant. Right, because these kind of scales that you've been looking at, these are very much like, I go up to the top of a hill, that's a human experience, right? Or stuff in a pipe, stuff in a car, that's a human experience. So how does the planet generate momentum? And more importantly, what powers a hurricane, right? So that kind of question happens in this Navier-Stokes momentum equation, but the term isn't even present, right? So there's extra terms we can add. But I think in order to do that well, we have to finish the thought about, so we've conserved mass, we've conserved momentum. What's the next thing we're conserving? And if you're a real fan of the mathematics, okay, if you're a real fan of the mathematics, maybe a third of you, then you may be interested in knowing that what we are doing is taking moments, okay? And what we mean by the moment of an equation or the moment of a quantity is we are saying, okay, there is a relationship. And the 0th moment is the one in which u to the power 0, the velocity of the power 0 shows up. times the mass. Not the mass, the momentum. What was that called? What's the quantity rho? What's the quantity rho u to the power 0? Good, that's just rho, good. That is the conservation of mass. What's the first moment? Good, that's rho u, right? Rho u to the power 1 is momentum, right? So we're going to look at the second moment. And that's rho u squared. Okay. So we already have the benefit of understanding what this quantity is. But if you were just a mathematician, you would be finding out the different ways in which we could do this consistent with all of the equations that we've had before, right? So we said that we need, in order to solve something like this, right? We said that we need to make simplifications, or we need to understand the ways in which these components fit with one another. Because over here, for example, I have pressure, and here I have density. How are those things related? Well, we did this kind of early and we kind of passed over it. What's an example of a way that I can relate P and rho? We ever related P to rho?
Definition of mass, I think I see just a question.
I'll give you the hint that you learned this in 2500 and 2510. That's exactly right. The ideal gas law is the very first type of a certain type of equation called an equation of state. And what we do with an equation of state is we take physical properties, macroscopic properties of a gas or a fluid, and we relate them. So the equation of state for an ideal gas relates the pressure, the temperature, and the density, as well as using the fact that you have some properties of the gas, the mass of the particles, for example, right? And you say in an ideal gas, I know how to relate these quantities. Now, we don't always use ideal gas, sometimes we're using fluids. So you might say to yourself, well, what is the ideal gas law for a liquid? Right? How do I relate the pressure to the density? That's the question. And of course, for some gases, for some liquids like water, for example, we can exist in a regime in which the density is constant. So the density does not depend on the pressure. That's a perfectly good equation of state that helps us simplify our solutions, right? In other cases, it's not so simple. And for example, you saw with an adiabatic gas, you may have seen something like this. P rho to the gamma is a constant. That's another equation of state. Because what we're doing here is we're relating these properties to a property of the fluid, a specific case, such that if I find it at one location, I can find it at others. And what this helps us do is it takes these things here, they're related, and it says, okay, I have a number of unknowns here. I have the momentum that's unknown, I have the density that's unknown, and I have the pressure that's unknown, right? Gravity, let's hope that that is described everywhere. Hopefully that's not an unknown that we're solving for, right? And everything in here, those are just velocities, and these are just properties of the fluid. So what we're trying to do in order to make this solvable is reduce the number of unknowns by tying them to themselves. So if, for example, I can simplify this and put it here, or simplify this and put it here, that's going to help us, okay? Yeah? Okay.
Yeah, it's a property of the material, right, or the gas?
Of the fluid, yeah. So it'll depend on whether or not you have a diatomic molecule or a single atom, right? It has very much to do with the physical properties of the gas, thermodynamic properties. Okay. But the ideal gas law is a little tricky, right? So here I just related the two and we said, oh, that's super easy. It's equal to a constant adiabatic. What does adiabatic mean again? Oh, shit. Oh, fuck, I forgot. Yeah, I would say most of that, like 85%. I would say no heat enters or leaves the system, right? I know, you're right in thinking about the molecules, but we really don't know the individual molecules, right? It's an emergent phenomenon. So what we're really thinking about there is no Q. No heat's being added or taken away, right? So that's really nice, right? Because then P and Q, they don't depend on temperature. They're just dependent on some constant, right? And so the P and Q are gonna move together really beautifully. But for your ideal gas law, how do you write the ideal gas law? P equals rho AT, something like that. And R is not fun because we don't use R, rho. PV equals nRT, but I don't have V, I have rho. So this is the ideal gas law, right? And there's a mu here if you want. This is the mean molecular mass, but I often forget it because I don't care. Okay. So this is really cute and I love this, but now the goal was to reduce the number of unknowns, and good job, Prismani, you added an unknown. Right? Now we have this thing that we have to consider, which is the temperature of the gas. And considering, for example, that we are breathing in a perfect gas right now, if we want to model, say, air in a room, then we're going to need to be able to describe the temperature, right? So in both of these circumstances here, we need a caloric equation of state, whether it's for solving for P or solving for rho, because they both depend on T, right? So this caloric equation of state, caloric meaning of energy, not of Dr. Caloric. And we need a conservation of energy statement. Okay. Where we're headed makes sense? Kind of. So let's try it. How do I give energy to the fluid? Okay, good. So that would give it momentum because forces and momentums, we have to be very careful with our words, right? So you're right that like, you made that hand motion. Right? I like the hand motion because that kind of communicates even more than the words do, right? You're like, I'm moving it. And so if I'm moving it, then I'm doing something to it. The forces themselves give us energy if they do what?
You know, if you rotate,
How does rotating?
well, accelerating it, circle, like, that can increase the energy because it's contained still in that space. But there's velocity.
You're giving it like rotational energy.
Yeah,
Okay, so you're thinking now about kinetic energy. I like that. You're thinking maybe about moving it, which I can think of as kinetic energy as well, just like linear kinetic energy. But I also want to think about how we do that. What was that? Work. Right? It's not just the force, it's the force what? Over a distance, right? You have to do an integral. Okay, so let's set up our integral formalism really quick and we'll see if we recognize any of these terms. So we have loved, we're just deeply in love with this format where we do ddt of an integral over a volume, right? And we're thinking about our parcel. But now I'm going to be a little weird about this, so I'm not just going to do this piece here, right? I claim that we're going to take the second moment, but I'm going to add this little thing called e. And this is not the natural logarithm. Okay, what is this? We ever seen this little e before in our whole life? Do we?
seen it in vectors,
Like a basis vector?
yeah.
Yeah, that's not quite what I wanted to go for. But you're right that that would be e in another language. Yeah, I'm saying it's not that. Oh, it's not that. Yeah. Okay. What makes sense when we're thinking about the second term? What's the second term? I've written it so it's provocative. What's that? What's this here? What's that?
Use, energy, right? Oh, wait, no.
U is velocity, right?
Let's get that.
1/2 velocity squared is kinetic energy divided by the right? So if you were just talking about a ball, right? You're just talking about a ball, and you said 1/2 u squared, that would be ke divided by n. Right? Okay. So then if I look at this piece here and I say, wait, I have a row here, 1/2 u squared. And remember that those are absolutized the vector. Okay. What the magnitude of the velocity? Okay, so that looks a lot like what? There you go. Of the fluid, right? So what's E? That's a great instinct, potential energy of the fluid. And we'll see on the right-hand side how we make kinetic energy and we make it from potential. But this is slightly different because I'm not talking about a ball. I'm talking about a jelly of gas or a jelly of fluid, right? So I get to do something different with that jelly.
The only thing it says potential has to do with gravity.
Yeah, all the potential terms are gonna come on the right-hand side in about 10 seconds.
Oh,
So on the left-hand side, we want to think about this really is what we can do to the fluid. On the right hand side is how we did it.
Be when it's steady.
What's that? Yeah, it's steady and then in the advective, right? That's like the idea here. We haven't broken that down because we haven't distributed this dt in yet. Normally it's dt and it's just the property like rho or rho u, but I'm adding an e plus. And I want us to understand why the e plus is so important.
Something initial about
Yeah, what is the, so let's take a fluid at rest. Okay, does it have energy?
storage.
Yeah, how does it have stored energy?
I don't know. I never thought about it like that.
Potential energy.
Well, let's think, I mean, let's go back to your idea of like individual molecules. Okay, what's special about individual molecules? If you have some gas in this room, can it do work?
If
Molecules, you mean?
Yeah. Yeah, right, why?
Moving around.
Because they're all moving around. So even at room temperature, right, you could take that gas and you could bring it somewhere else. Let's say bring it under a pool, right? And it would rise or it would change, it would expand whatever balloon you're in because those individual molecules are moving. So unless the thing is at absolute zero, it has internal energy. That is your little e. Your little e has everything to do with the motion of the molecules inside of the object that you're seeing. Not bulk, not how they're moving around in the fluid, but is it warm? Is it cold? Is there a lot of pressure, right? That type of internal energy. Okay, so little e is the internal energy. And we did this sort of at the beginning of the semester. We had these like thermodynamic equations, and we use little e there. Little e is different from big E. Why is that?
per
Per, right? So this is a per quantity. If I multiply the density by the internal energy, the little one, then I get the total. As opposed to, like if you have some quantity of gas here, okay, and you cut it in half. The total energy goes down by half in each, but the internal energy is the same. Right? It doesn't matter how big the volume is. That makes sense. Okay, so we understand this left-hand side?
I feel like little e has like other variables that are attached to it, like you said.
Yes, yeah, no, absolutely, that's baked in, and I'm hiding it, right? So, you're right, that's a very good instinct, right? Because you're like, wait. So we are thinking just right now about conservation of energy. And once we do that, then we'll be able to relate it back to our equations of state. Because our equations of state are going to describe how we think about the internal energy in the object. Right? And what we're about to see is I said on the left-hand side that this was the changes to the properties of the thing. And then on the right-hand side, I'm going to show you what makes those changes. But I want you to see something just right away. The fact that there are two terms here means that I can do two things with any of the forces or choices on the left, on the right, right? So let's take, for example, this idea of work. Okay, let's do work on the parcel. I could change the internal energy, or I could change the kinetic energy, right? And you see there that that is a choice, and it's going to be dependent on what we do. Does that make sense? Some things will change the internal energy without increasing the kinetic energy.
Like heat, like temperature.
Like temperature. But even paradoxically, I can create motion over here that doesn't increase the motion of the gas, but heats it. What would that be an example of? It's okay if you don't have this one right off the top of your head. It's kind of a weird one. So we're gonna take, we haven't seen the way that we created it here, but I'm gonna tell you, like, what if we had some ability to use motion, but it doesn't create kinetic energy, it creates internal. Yes, I think that was like a very similar answer, because you both thought about temperature. What's that?
So like they're saying like heating something.
They're saying like heating, like applying Q. And that's not wrong, right? Applying Q can certainly create internal energy. But that I'm trying to say is there is a way, and you know this way, you just don't know it yet. There is a way to take motion and turn it into internal energy. And it is so ingrained into you, you've never thought about it.
Say, like collision.
Collisions, good. What are collisions a version of? You're thinking right. You're thinking about the fact that you take motion, you smash into it, and now you're thinking about the molecular level, and now those molecules start moving faster, and that is what we interpret as increased temperature or heat. But what is that process?
Let me say you know that. Oh,
Ready?
give us what it starts with.
Ready? Ready? Are you ready or not? Friction. Friction takes motion and doesn't create motion, it heats. Right?
I'm thinking like also like if I have an inelastic collision where like these two are hitting at the same speed and they stop, it's
Mhm.
also the same, where they transfer energy, but I guess like they both heat up, I guess.
Well, they must, right, in order to conserve the energy,
Yeah,
right? So if there's two things coming at each other at 60 miles an hour and they stop, they either deform, breaking chemical bonds or something like that. But if they're two molecules, and they hit into each other and they stop, they must individually become warm. And maybe they turn into rapidly like thickness. So this is a way to take motion and turn it into internal energy. You'll also learn about something called eddies. Okay, eddies are a great way to take motion from the fluid and turn it into internal heat. Because what you get is something called turbulence. And instead of motion, say going from the edge of the screen over here, like this, let's say you run into an object and you curl around it, you start to create this little whirlpool. The funny thing, we think about streamlines, right? We think about these streamlines that go all over the fluid, and they connect from point A to point B, they go out of the fluid, or they start in the fluid and they come back to where they started. How would an eddy be visualized? Because in fact, what ends up happening, they curl in themselves all the way until you can't resolve them. And what you're really doing there is you're taking large motions of the fluid and you're turning them into motions of the molecules, heating them. Okay, so that was a tirade. I apologize for the length of that. Let's think about all of the ways in which we can generate energy, both internal energy and kinetic energy. You said one already. That's it earlier. Breathing temperature. Good. So that would be the third one. I'm gonna write it here. I'm gonna say A Q dot N. Okay. over some area. So to raise the temperature of a parcel, I can heat the surface of the parcel. So in order to make my ramen late night, okay, I put my pot of water over the fire. And the fire applies heat at the bottom. And that heat passes through the metal, heating up the metal, and then passing through the bottom surface of the fluid. Right? And once I've applied the heat there, then it can move around within my pot. Okay? Good. What else?
Change.
Excuse me?
Increase the pressure with.
Okay, on the left-hand side, I'm just thinking about ways to generate energy. What? Transfer what? That's right there.
Change the height
Change in height of what?
through gravity.
If you consider gravity, right? That would be what we call potential energy. So we can have a term for potential energy if we raise or lower that pot of water, right? If I raise it up and then I drop it, it certainly is going to gain kinetic energy, right? So I can write that here, and that's going to work on the entire volume. Rho G, which is another vector, dotted into U, dV. Good, and now we're just missing one. This is the one that we started with. It's already mentioned at the very beginning. Work. Work, 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 work. All right, so let's do that over the area. Okay, that's a force dotted into the velocity over some area. Okay. So how do I interpret those three terms?
I'm curious as to why, the temperature one is negative.
That's just a convention with the way that we write Q, in or out of the system. Right, so like dVt, the positive here. So if this is positive, then the rate of change of the energy has to be Q into the normal. And remember that the normal always points perpendicular to what? The surface. So think about the thing, right? So if Q is going this way with the normal, right, if they're dotted, then which way is the Q going? In or out of the system?
Out.
Out. But if it's going into the system, then they're perpendicular to one another, and this dot product gives us a negative here, and a negative times a negative is positive. Okay, I guess I didn't need to say no, do that right away. Okay, so what are the three terms?
You have those or a combination of those, we can generate energy.
Yes, but what does each one mean? Let's just say them again. What is acting on all body? Gravity, right? Body forces acting on the whole body. Good. Second term? I mean, yeah, I like work. And in fact, let's be very specific here. This is the work done by gravity. This is the work done by
Us.
I can raise it once.
Like the pressure.
You're first moving. Yeah, the surface forces, right? So the main distinction here is these are body forces that are doing work. These are surface forces. Okay. This is the easiest one. Boom. Okay, so what did I do here? Let's write these ones again. What was this? Internal. This one here? Kinetic. Okay, so this whole thing is? Yeah, let's just say energy. Yeah. Okay, so look at how complicated I made it. Right? And all I'm saying is the energy comes from the work done by gravity, the work done by surface forces, and the heat. That's a statement that we've made in the beginning of the semester, right? Talking about DQs and E's and right, those W's. W, Q, E. That's all I'm saying. E, W, Q. But now we can do it for fluid. Okay. You love it? Helpful. Okay. So this is where it starts to get a little fucked. Because now we actually have to do it, you know, like describing all of the different letters in detail and thinking in particular about this one. Okay. This is the one that's gonna give us. Because what was the F that we used before the Navier Stokes equation? Yeah, we used this F before, didn't we? When we were deriving
Have like capital F for effective, but not.
little F. Well, little F was our stand-in for our stresses. Right?
Oh, yeah.
What kind of surface forces?
Yeah.
This is gonna be our stresses and our strains, right? And that's the one that has all those fucking derivatives in it. So we need to think about how we combine this in tensor notation to account for all the stresses, right? Let's see if we can do that. Yeah, we're doing a lot. Do we want the derivation? You want to go from this one to the may apply this here. Get the two terms. Did it all together, it's a lot of math. Pretty dull. Pretty annoying. Hey, yo. Alright. Let's try the first piece. I'm not gonna rewrite the second piece because it's gonna be the same. But make one change at a time. So the first piece is straightforward. I'm gonna apply this derivative. We're gonna apply this derivative here. So we're thinking about some arbitrary control volume V, some jelly beans moving around. And we can write this. We can write this by putting this piece into the integral, so taking it for each of these. So you'll have something like the integral V of p dt. This is a partial now instead of the one that we used before. Rho e plus rho over 2 u squared dv plus recall that when we use Reynolds transport theorem, we think not only about the change in the volume itself, but also stuff that might be passing through the surface. So in order to do that, we now have a second term, and that is the area integral. And that area integral, we have to think about the normal to the surface of the area. So you're just gonna have something like rho e plus rho over 2. This is the same thing as before. But now, and here's the important part, you have something like the advective term going through the surface. Right? That's advecting through the surface versus the time rate of change of this quantity. Okay. We like it. So that would be what this term. It's a lot of letters, but it means the same thing. The time rate of change of the internal energy and of the kinetic energy. And all I've written in here using the Reynolds transport theorem is that this is the same as the time rate of change of the internal energy, or the time rate of change of the kinetic energy. And any internal energy that leaves, or any any kinetic energy that leaves. Right? Advection. Get that piece. Okay, so okay, I'm gonna now write all of my see these ones here. I need to convert them into volume integrals. Because the way that we did this before, you recall, is that let's say I take these things to be true over some arbitrary volume. If all of them are true over an arbitrary volume, I can take them and I can put them all on the same side. And then they'll be equal to 0. And the only time the integral of something is equal to 0 is if it's also 0. The integrand, the thing you're integrating, must be identically 0 at all points within the volume. So the goal here, and the thing that we try and do each time when we apply these, is to think about some control volume with stuff going in and out, do the bookkeeping of the different ways that it can happen. Then we convert using the Reynolds transport theorem, apply these interior pieces. We need to use here Gauss's theorem or Stokes' theorem, depending on which way we're going, to go between an area integral and the volume integral. Those have a similar concurrence here. So if we can convert these three and make them all volumes, then we're good. Okay, so I'm just going to do 3 in a row. And we love it, right? Okay, so let's do this one first. And I'm just gonna write the answer, I'm not gonna rewrite it. Try not to be a masochist. Okay? So this one here, you would write as the volume integral of dx of the internal energy E plus 1/2 U squared, and I'm writing it in tensor notation too. I know you guys love that. UI dV. Okay. So what I really would have said here is that this piece, anytime you see ddxi ui, that looks like the divergence, right? Because this thing is dotted into this one. Okay, so now let's take this guy here. Let's bring him all the way over here so I have room. So this is, and I can rewrite this one because it's small, the integral of f dot u dA is equal to the volume integral. You'll recognize your favorite friend here. T I J U J E. Okay, then we just have one more piece. So I can write this one and the integral over an area of Q dot N dA. But that is simply the integral over a volume of d dx I, oops, it's not Q. Q I, yeah. A lot, right? I haven't said anything new, or we haven't changed what these terms mean. This is still the changes in the internal energy and the kinetic energy. This is still the work done by body forces. This is still the work done by surface forces, and this is still the work done or the heat added to the system. But this is the way we write the heat. So what this means is, right, d dx of q, these are gradients of heat. If there is more heat on one side than the other, then heat goes from the hot place to the cold place. That's the easiest one to think about, right? This one will give us nightmares, because again, it's got this fucking stress tensor. But this is the rate of spatial change of the stress tensor in the direction of some fluid velocity. So how is the stress tensor adding energy? And this one here, you're gonna be fine with this. Just our effective term. We know, right? But it's the effective term of internal energy and kinetic energy. Okay.
Right side. But you were saying that that's.
Yeah, this is just heat transfer. And we can just think of this as spatial derivatives of the heat, which you can think about as being like you have your pot of water and you have hot on the bottom and cold on the top. So heat is going to go in. Right? That's the basic. Okay. Yeah.
And then rate of spatial change due to stress. Or? Or is it? 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 Or is tensor? or-
This one here?
Yeah.
Yeah, so this one here is the way in which stresses in the fluid are gonna create heat. But the mechanism for that is because, there needs to be spatial differences. So if the stress is uniform, right, there's no spatial differences, then there's no heat transfer. So just like we had over here, with some spatial differences in the heat, you need the spatial differences in stress. Okay, we happy? Or at least for like not right? Okay. Okay, so let's write out the hardest part. Okay. It's this one. Okay. Running out of space here. Okay. This piece is long, but I'm just gonna write it as minus P times duj over dxj plus tau ij duj. Oops. This one. Oh, it's down here. These two match, these two match, these two match. This is the, what we've done here, remember, is that the generalized stress tensor, Tij, can be broken into one that is the pressure on the diagonal, and the off diagonal terms are dealing with tau, right? So we're separating them so we can see and kind of understand them better. Here, it's saying this is the work done by the pressure terms. Here's the work done by the stress terms. Okay. So that's the first part. If you can believe it, there's two more terms. Okay. And it's minus uj dp dxj plus uj d tau ij dx. Okay.
The first sub J and X sub J?
Sorry, which one?
That
This one?
first, yeah,
It's J and J.
I thought they went back and forth when you did, I thought the use of I,
Well, have a look here. See the I, J, J. So this by definition can't be a vector quantity. This has to be summed over all of these indices so that no index comes out. Because if you look up here, this is a scalar. It's a scalar on the left-hand side. So each term has to be a scalar on the right-hand side. Right, so Q dot N is a scalar, F dot U is a scalar, G dot U is a scalar. Right? So even by the time that we come from here, we bring it all down to here, all of a sudden we see all of these different components. They still have to give you one number at the end. The contribution, each term within that number might be wildly different in the way we interpret it, but it still should be one number in terms of like joules. Right? 74 joules. That's the contribution from the viscous heat. So this one here is pressure heat. This one here is heating due to viscous forces. And then these two here, these are the ones that are going to give you 9. And you're going to look at them and you're going to say, what's the difference, right? It's P du, U dP. Right? They should be the same, but they're not the same. Okay?
I just don't have on that notation, I know I'm supposed to change X of I to X of J,
Where? Here?
yeah,
To go from here to here?
yeah.
I mean, I'm skipping steps, right? Because I'm writing it, you need to write out what Tij is.
Okay,
And you would need to write Tij out as P plus tau ij. And then as you go through that process, you collect terms. So you're gonna have these are when you do it yourself, these start on the same side. And you'll see here that the JJs and the JJs, this comes from the Kronecker delta. Because it's not just minus P, it's minus P delta ij. And that converts the I to the J or the J to the I. Right, I could have easily have written this DUI, DXI, and that would be fine. The
Okay.
choice of J doesn't matter. They're gonna be summed over. Is that okay? Okay. I think I've said this all right. Taking the difference between this and the previous one. Oh, okay. Yeah, any good here today? Let's see. Um. I'll just write it here. So we are thinking, let's just, sort of remember why we're doing all of this in the first place. We're trying to answer the questions about the internal energy, right? And Kevin pointed out earlier, well, doesn't that just add new unknowns? So for example, we were trying to think about things like P and rho and T and how they're all related to one another, right? So if we, I'm gonna skip quite a few steps here, but we can essentially rewrite this whole big nasty equation using the total derivative and focusing just on the internal energy and subtracting off the momentum terms. So for example, here you notice that there's something like the velocity squared. So you could conceptually think about how you take your momentum terms, right? And hit them with another U, and then see what you can take off, just so you only have the dt. And we can do this if we have more time at the beginning of next class. But it ends up looking like this, and it's really beautiful. It's dE dt, the total derivative of the internal energy, is equal to minus P big D dt of, we call this you remember this is the specific specific density, which is 1 over the density. I'm just gonna write it like this. That'll be simpler. Plus 1 over the density tau ij s ij minus 1 over the density x I q I. Okay. So what have I said here? I just said that the internal energy changes due to a contribution from the pressure forces, a contribution from the viscous terms, and a contribution from the heat added, right? Which is more or less what we said up here, except we haven't discussed how the energy changes. Okay. And sorry, the kinetic. But this is essentially where we're headed. So this is the total derivative of the internal energy. And now the question is what is the total derivative of the kinetic energy? Because once we can isolate this, you see this E that we wanted before, we have our own equation. And it depends solely on things like P and rho.
right? So as long as we have that caloric equation of state, then we can see how that caloric equation of state is going to change based on the variables that we can measure. So if we were just thinking about doing this on a computer, right? Let's say you have some box. And every cell in that box has properties like the velocity, temperature, the pressure, etc. Right? Then you can see how the internal energy is going to evolve due to whatever's happened. Right? And you can simulate it. So in the next one, we'll talk about the total change of the kinetic energy, and then we'll have all of our conservation laws. And all that's going to take, really not all. So we'll have the conservation of mass, of the conservation of momentum, of the conservation of kinetic energy, and then we'll have our caloric equation of state, and then we'll be good. Okay. Isn't it fun how few slides we get through now?